talked about the forces of lift and drag when we discussed the four forces of flight. Now we'll discover the quantitative aspects of lift and drag and how that impacts the performance of our aircraft. If you remember from our last presentation, there are two things that affect lift. The faster you travel with the same aircraft, the more lift you get. Additionally, the shape and orientation of the airfoil affects the amount of lift. More of an angle to the same airfoil gives more lift. Think about deflection. But also the specific shape of the airfoil affects lift. If you compare two different airfoils, the one with the greater camber is going to produce more lift. Think about Bernoulli and Coanda effects. We will discuss the Reynolds number, which takes into account the relative velocity of the plane as well as the length of fluid flow around the airfoil, which allows us to extrapolate and compare airfoil performance. Remember, the Coanda effect works by creating a boundary layer around the surface of an object, whereby fluid or air molecules stick to the surface of the object. Due to this sticking, there is a section of slower moving air closer to the wing. The molecules increase in velocity as you get further from the wing. The boundary layer is critical to changing wing and aircraft performance. You can find more information on this on the NASA Reynolds number webpage. The angle of attack is the angle at which the airfoil comes in contact with the air. Remember, generally, a greater angle corresponds to greater lift. However, there's a critical angle of attack at which the airflow becomes turbulent. Airflow separates from the airfoil and lift decreases dramatically. NASA developed an applet to show how the angle of attack impacts lift. It can be accessed through the link shown on the slide. Training planes have a long window before stall at the peak of the graph. High-performance planes may have a very sharp peak at this location. So pilots must know their plane well and where that stall location is, especially if it's a life or death situation, like with fighter jets. We can relate the boundary flow to angle of attack and thus the amount of lift achieved. Airflow around the airfoil remains smooth and steady until we hit the critical angle of attack. At this angle, airflow around the airfoil becomes unsteady and turbulent. When this happens, we reduce the amount of contributing lift due to the Coanda effect, thus causing unsteady flight or potentially dangerous stall conditions. When objects move through a fluid, it disturbs the molecules. When an airfoil moves through air molecules, the motion generates aerodynamic forces. The Reynolds number gives us the ability to relate the fluid flow around similar objects. Remember, the two things that generate lift are shape or angle and velocity. We can set the Reynolds number of two airfoils equal to one another to relate the velocity and shape or size of the airfoil. Mathematically, the Reynolds number is the ratio of inertial forces to viscous forces. What does this mean? We're comparing the mass times velocity of the traveling fluid, or air in the case of aerospace, to the viscosity of the fluid, air. Note the density has a unit of mass built into it. The Reynolds number is a dimensionless number that is usually a very large number, in the millions. The Reynolds number is equal to the fluid density times speed times length of fluid travel divided by the fluid viscosity. For aerospace purposes, fluid density and viscosity will be that of air. Velocity will be that of our aircraft. What will be the length of fluid travel? That will be the length of the path of the air as it travels around the airfoil. Remember, more camber to our airfoil gives us more lift. Why? Because it increases that flow path length. Increasing the flow path length increases the time the boundary layer is in contact with our airfoil, allowing more pulling force or lift to be generated. This is how we can use a wind tunnel to compare the characteristics of a model airfoil or other device to a full-scale model. Sometimes engineers can't get the air in the tunnel moving fast enough, so they can apply this practice using water. Water has a much greater fluid density and viscosity, so they don't have to get it moving as fast to achieve the same testing conditions. Let's apply this equation to a problem. A P-3 Orion is cruising at 820 kilometers per hour, 509 miles per hour, at an altitude of 4,023 meters, or 13,198 feet. Assume a fluid viscosity coefficient of 1.65 times 10 to the negative 5 newton seconds per meter cubed. What is the average Reynolds number along a wing cross-section measuring 1.1 meters or 3.6 feet from leading edge to trailing edge? Can't forget about the atmospheric properties we learned in the last lesson. Remember, with altitude, the temperature and pressure and air density change. So we use our equations assuming standard conditions at ground level to calculate temperature and pressure. Then we insert our temperature and pressure numbers into the density equation. We need to convert our velocity into appropriate units. Remember, our equation uses meters per second. Then we can calculate Reynolds number using the density and velocity found previously. We get a Reynolds number of about 12.4 million. How does that compare? A seagull has a Reynolds number of about 62,000 and a paper airplane is about 47,000. The coefficient of lift is an experimentally determined value which accounts for shape, angle, and velocity of a wing. Rearranging the coefficient of lift equation shows that lift is increased by wing area, air density, and velocity. Velocity is a squared function giving it a more significant impact on lift. A greater coefficient of lift corresponds to greater lift. Remember from our forces discussion, at equilibrium, the lift must be equal to the weight to maintain altitude. So in this equation, you will use the weight of the aircraft for lift. Again, make sure units are consistent prior to using the equation, meaning you can use SI or customary units as long as they correspond throughout the equation. Let's work through an example problem. The Cessna 172 from activity 1.2.2, step number 2, takes off successfully from Denver, Colorado during an average day in May at 22 degrees with a standard pressure of 101.3 kilopascals. Assume that the takeoff speed is 55 knots or 102 kilometers per hour. What is the minimum coefficient of lift needed at the point where the aircraft just lifts off the ground? The Cessna wing area is 18.2 meters squared and the weight is 2,328 pounds or 1,056 kilograms. Weight is the force due to gravity pulling the plane towards Earth. So we must multiply the mass times the acceleration. Keep in mind, if we're given weight in pounds, this value already accounts for gravity, so you don't need to multiply. Then convert to velocity from kilometers per hour to meters per second. Determine the air density using the air density formula for temperature and pressure. Then apply the coefficient of lift equation, and you get 1.19. Again, notice this is a unitless value. The coefficient of drag looks just like the coefficient of lift equation, but evaluates the amount of drag on a wing. It's again determined experimentally and takes into account shape and angle of attack. Our equation refers to wing area to directly compare our coefficient of drag to our coefficient of lift. But the area of reference within the coefficient of drag can vary depending on what the coefficient of drag is compared with. You can evaluate drag with respect to total surface area, frontal area, or wing area because they're all proportional to one another. The shape of an object affects the drag. We're going to select a wing shape that provides an appropriate amount of drag for our purpose. Think about this in relation to the use of flaps. Throughout the flight, we'll modify the arrangement to increase lift or drag depending on our desired condition. Let's apply the drag equation to a problem. The same Cessna 172 from activity 1.2.2, step number 2, takes off under the same conditions as described earlier in this presentation. How much drag is produced when the wing configured such that the coefficient of drag is 0.05? First, we'll rearrange the equation for drag, capital D, by multiplying both sides by A rho v squared and then dividing by 2. We will insert the values for all the variables, again making sure they're in the corresponding units. We get a drag of 436 newtons. The pressure difference above and below the wing can cause airflow that is perpendicular to the main airflow over the wing. This causes a flow that's both upward and rearward, causing the air to form a vortex. This can be seen on some aircraft at slow airspeeds in high humidity conditions, like at takeoff and landing. This will decrease available lift and increase drag. Bigger planes make bigger vortices, so in a large commercial aircraft, this could significantly affect performance and efficiency. The best way to prevent these vortices is to not have a wingtip at all, but obviously this isn't an option. So winglets were invented and implemented to simulate the condition of there being no wingtip. Winglets are vertical airfoils on the end of the wings, which significantly reduce drag due to vortices and improve fuel efficiency. Additional information.